So by now you should have downloaded or printed out paper that looks something like this. Mine has holes in it to try to keep the left and right side oriented for you. But what we're going to do together is we are going to create a scale model of the atmosphere. We're basically taking notes together. And your job is at the end of this video is to upload your completed scale model and show me at the end. I'm going to use this overhead screen behind me to get started here. Now I'm going to use a whole bunch of different colors. That's just the way that my brain likes to think. You don't have to use the same colors as I do. But you do have to complete this with me, because at the end of this video, you're going to have to upload your graph and show me the notes that you've taken. So like any good graph, we're going to start with a title. This one's going to be the atmosphere. Now the way I've held my graph is I put the title at the top with that blank space looking like a big blank letter L on the left side and on the bottom. That's where we're going to need our room. And it's a scale model of our atmosphere, so we are creating something from the ground up. So right here along the ground, we're going to call this 0. That'll be 0 kilometers above the ground. And now every dark line, we're going to increase that number by 20. So 20, 40, 60, and so on. If you do it correctly, you should get to 200. Now, any math teacher would just despise me for what I did, because I put a bunch of numbers down and I didn't say what those numbers meant. So let's take our paper and turn it to the side, and we're going to label this axis. This is the distance above the ground. And any good math or science teacher will make you put units in here. So we're going to keep it metric. What the rest of the world uses, we'll call it kilometers. Once you're done with that, we're now going to find 3 additional heights above the ground, starting with 10. 10 is going to be halfway between 0 and 20. Each little line's worth 2, so it's 2, 4, 6, 8, 10 would be located right here. The next one we're going to look for is 50, which is halfway between 40 and 60. And the last one we're going to find is 85. Again, each little block is 2, so it's 2, 4, it'd be right about there, 85. Now I'm going to use the same color, but I have a big thick marker here. And what we're going to do is we are going to darken in that line at 10, like we just labeled, so it really stands out. We'll do it again at 50, and again at 85. It doesn't have to be perfect, just close. Our atmosphere consists of 4 distinct layers, and that's what we've labeled. A skinny one at the bottom, that's 1, 2, 3, 4. What I'm going to do is I'm going to switch colors to my blue pen, and we're going to use these first 3 columns on the left. In this space, I'm going to write what each one of these layers is and what it means. So we'll start with the uppermost layer, right up here around 160. This layer is called the thermosphere. That's a little bit of Greek, literal Greek. Thermos is something that we use in the English language all the time. A thermos is something that keeps our drinks warm. A thermometer or a thermometer measures heat. So I'm switching colors again, and I'm going to indicate that thermosphere is the heat sphere. The atmosphere surrounds our globe, and our globe is a sphere, so our atmosphere is also going to be a sphere. The thermosphere is the outermost layer. Let's move down now these columns, and we're going to go to this middle layer right here. This is the mesosphere. If you take part in a choir or you've ever played a musical instrument, dynamics are listed in your music. Loud is indicated with the letter F, that's forte. Soft is a little letter P, that's piano. But if you want it to be a little louder than soft, somewhere in between, or a little softer than loud, a little in between, you would put an M for mezzo piano, mezzo forte. There's singers who sing very high who are sopranos, and those that aren't quite as high are mezzo sopranos. So mezzo is just a prefix for middle. It's the middle sphere. Which is weird when we're talking about 4 layers. How do you get in the middle of the number 4? But really, it's the amount of space it takes up and where it's located in our atmosphere. If I zoom out, you can see that the mesosphere is located right there in the middle of the page. Below our mesosphere is our next layer, the stratosphere. Now, this is a trickier prefix to talk about, that word strato. It's in the word stratus, which is something that's flat. I guess it's close to the word straight as well. So our stratosphere, strato is flat, and the reason why it gets that name is because of the winds in this layer. This is the layer of straight, fast wind. Flat, straight, fast wind. How fast? We're talking about 300 miles an hour. That leaves us with our bottommost layer, the one that we live in, all the way down here. The bottom layer is called the troposphere. This is the layer of the mixed wind. It's not the straight and fast wind. It's mixed around. We have wind that blows into the page, out of the page, up and down, around in circles. It's going all sorts of different directions here. Where in the stratosphere, it's consistently going in one general direction. One fact about the troposphere, all weather that we're going to talk about in this class, well, 99.9% of it is here. And all life and most air is here. We have 4 different layers of our atmosphere because each layer is distinct. It has something unique about it. One of its physical properties is unique. And we've been talking about physical properties so far in this class. So I'm going to slide all the way over to the rightmost column. And I'm changing my pen to a red color. You don't have to use red. You don't even have to change colors. But I think it just makes it a little bit easier to see. And it's a very exciting time in this class for me, because I'm about to talk about one of my favorite laws of science. Something so important for weather that we're going to use it over and over and over in this class again. Here we go. The sun heats the ground. That seems simple. The sun heats the ground, no kidding. But that's how the earth gets warmer. The sun heats the ground first. Then that ground ends up heating the air. The sun heats the ground heats the air. The ground is like an oven. So I'm going to draw that there in that last column. Here is the heat source, what makes everything warm. And that means right there along the ground and everything next to it, this is the warmest layer. We're talking about the physical property of temperature. Once you leave that heat source, it's only going to get colder. So the stratosphere, that's colder. As we go to the mesosphere, it's even colder. So you remember that garbage can, that one back there that I said you didn't want to look inside of it in the previous video? Well, now I'll tell you what's inside it. Lots and lots of Justin Bieber CDs. So this is what I feel about that. That's now going to be our sun. There's a flame back there and it's pretty hot. But actually, I'm very close to the earth right now. The sun is heating the earth and the earth is giving me my heat. I'm very close to it. So I'm really warm right now. But if I go to the chair back there, now I'm a little bit farther away from the earth. I'm not feeling the earth as much, but still it's more than my sun that is well behind me until now I'm really close to the sun. I'm feeling more of the heat from this fire than I am from the earth. So there's got to be a point somewhere here in between where I stop feeling the sun and I start feeling the earth. Or the other way, I stop feeling the earth and I start feeling the sun back there. That spot is the top of the mesosphere. So as we demonstrated, that spot between where the sun is affecting our heat and the earth is affecting our heat is right here at the top of the mesosphere. That is the coldest spot. And this spot that I'm putting a red star next to determines where the top of the mesosphere here is. The mesosphere's ceiling is defined as the coldest temperature in our atmosphere, or the spot directly between where you're feeling the heat from the earth compared to the heat from the sun. Once you go above that coldest spot, the temperature only gets warmer as you get closer to the sun. That's why this layer is called the thermosphere or the heat sphere. So I'm going to draw an arrow like this, and I'm going to say it gets warmer as you get closer to the sun. If it was just as simple as that, then we actually would only have two layers. We'd have a thermosphere and then something below it. However, there's something here smack dab in the middle that affects the temperature a different way. So what I want us to do now is find 25. At the number 25, I'm going to purple by the way, I'm going to put a dotted line across the page. This is the location of a very special thing, which we'll talk about a little bit more later in class. This is where the ozone layer is. Now what I'm going to do is I'm going to talk about how quickly the temperature drops in each of these layers. Yes, it's getting colder as we go up, but what's happening to how quickly the temperature goes down in each one of these layers? So as we leave the surface of the Earth, it makes sense that the temperature would drop. So I'm going to go ahead and get my purple pen, and in that second column all the way on the right, I'm going to go ahead and draw a big arrow like this and say it gets colder. And I'm going to jump up to the mesosphere and do the same thing. There's my arrow. It gets colder the exact same way. So something weird is happening to the stratosphere, and it's what's defining what the stratosphere is like. So let's go ahead and take a look at this another way. So let's say the ozone layer is like this candle, which puts out just a little bit of heat. Let's put this right here. Now, of course, this isn't to scale. Oh, my sun went out. Now, obviously, standing right here is going to be very warm. And standing right here is going to be warm from the earth. But there's a spot right next to this candle where I start to feel the warmth of the candle in this general region. This layer here is warmer than it should be, and this area is like our stratosphere. So the stratosphere exists because it's an area that's receiving some of that absorbed heat from the ozone layer. That goes from here down to here. And in this region, it gets a bit warmer. And I like to write that. Thanks, ozone. It gets a bit warmer right here. Sure, the temperature might be 80 on the ground, and it might drop to 0 here. And then it might go up from 0 to 15 to maybe 20. But 20 degrees is still colder than down here. So yes, this layer is colder than the troposphere below it. But the temperature drops quickly here, and this area is affected by the UV rays absorbed by that ozone layer. This defines the location of our stratosphere. It defines the top and the bottom of the stratosphere. And if you look at what we have here, the top of the mesosphere is defined as a temperature boundary. And the top and bottom of the stratosphere is defined as a temperature boundary. And what we're left with then are 4 layers of our atmosphere: the thermosphere, mesosphere, stratosphere, and troposphere. Now there's another physical property I want to talk about that we're not going to discuss until a little bit later in this class. However, I want to go ahead and take this column in order to put that information down. I'm going to use my brown pen. I'm not going to explain it very much, but we're going to look at air pressure. And right there on the ground is where we have the most air pressure. When we look at air pressure in the stratosphere, it is less. In the mesosphere, it's even less. And in the troposphere, it's almost 0. Let's add one more thing to our drawing in this last column right here. Notice I have the orange pen out. And we're just going to draw some things to give you some perspective on our scale model, because our atmosphere is thin. If we look at the highest mountain above the ground, Mount Everest, at times it peaks up into the stratosphere. That's why they need oxygen in order to climb Mount Everest. There's just not enough oxygen in the air at the top of the mountain. A hot air balloon does not go that high. Even the highest hot air balloons are only going to be located right there where that dot is. Not that far above the ground at all. An airplane traveling long distances, that's going to end up flying up here in the stratosphere. In fact, they use these straight, fast winds in order to increase their fuel efficiency. And thunderstorms. The biggest clouds on Earth are formed by rising air in the troposphere. This air rises up, and then once it gets up into this stratosphere where these straight and fast winds are blowing, the top gets cut off of these clouds. And you'll see this big, long panhandle or anvil shape to the top of the clouds. In the summertime, you see this all the time with thunderstorms coming in. You look up, you see this big flat cloud all the way at the top. You're actually looking up to the top of the troposphere and the bottom of the stratosphere. In the stratosphere, that's where we typically send up weather balloons. Weather balloons are not your standard hot air balloons. We'll talk about those in this class as well. So that's my hot air balloon. If you ever see a shooting star at night, they look like they're burning up close to the ground, but they're up here at the top of the mesosphere. And finally, all the way at the top of the atmosphere, right near the very, very top, is the International Space Station. I don't know what that looks like. We'll just say it looks like that. The International Space Station is hovering just above the top of the thermosphere. I've got a highlighter for one more thing that I want to mark, and it's going to be somewhere around 100, and it's not really going to be well defined. I'm just going to kind of put like a squiggle all the way across like this. And I'm going to get a pen, and I'm just going to label this the ionosphere. Wrote it very, very thin there, ionosphere. And it's key to remember that this is not a layer, even though it has the word sphere in it. This is just a pile of gas that are a bunch of ions. And this is going to be important for your activity that you have to do in the future. We discussed ions in class already. That's a charged atom, something that's not neutral as far as charge is concerned. Okay, so there we go. We've got ourselves a scale model of the atmosphere, and this is something that you're going to have to turn in as one of your assignments. Throughout this class, we're going to go ahead and take an awful long look at the different layers. In particular, we're going to pay attention to the bottom layer, the troposphere, because that's most of where the weather forecasting takes place. So we've created our scale model. This is a more professional one from a textbook company. And you can see here the layer of the troposphere, which says we have a decrease in temperature day to day. I'm going to point out this line right here. That is what the temperature is doing as it goes up throughout the atmosphere. Now notice as we look at the stratosphere, it stops decreasing and it starts increasing. That's the definition of what the stratosphere is, the area where the ozone is causing the temperature to be steady or increase. And then when you get up to the mesosphere, it drops very, very quickly, yet again, followed by the thermosphere at the top. What's really cool is the space shuttle took a picture at sunset in space, and actually you can see all 4 layers of the atmosphere in this photo. You've got a storm cloud there. Notice the flat top. That's marking where the top of the troposphere is, and the troposphere is bending the light that it looks orange. Then the layer on top of it, that green color, that's the stratosphere, and then the mesosphere is on top of that, followed by the thermosphere. Keep in mind how big that Earth would have to be for the atmosphere to even be that thick. Okay, you can't even see the curve of the Earth in that photograph. The internet is full of people who have created balloons and have sent them into space. This is one of the first ones that we had. Back in 2008, they set a camera up and they had a tracker on it that when it landed they could find it. And it's amazing how quickly it takes for you to go to space and back with a simple weather balloon. This video runs for an hour. I went ahead and I edited it down so it's not going to last so long. But let's watch this and you'll see just how quickly it takes for you to get to space. There the balloon is burst. and then it falls all the way back to the ground. Coming up in this video, you're going to see them on the ground at an intersection. It's going to go by quickly, and the video warns you that it's coming. It had a parachute on it, so the camera wasn't affected. That was 2008. Nowadays, they are everywhere on the internet. This is one of the best ones, I think. It's from Danny Dover, and he has some drone footage, and he'll take you through the steps of how he makes this spacecraft. I thought this would be an effective way to end this lesson, so you can see how long it takes to get out of the atmosphere. It's really not that long.
Audio 12. 12, Tony, stand by for my mark at 20 seconds. Stand by. Mark. Stand by for 10-second countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
This is ground control to Major Tom. You really made the grade, and the papers want to know whose shirt you wear. Now it's time to leave the caption, if you dare. This is Major Tom, the ground control. I'm stepping through the door, and I'm floating in a most peculiar way, and the stars look very different today. For here I'm sitting in a tin can, far above the world. Planet Earth is blue, and there's nothing I can do.
What's going on?
What's the big lesson from this? Our atmosphere is thin and fragile.